Hello class, good morning. So in this lecture video, I will be discussing free fall, another type of motion happening along the vertical axis. One example of this motion is an object that is dropped from a certain height and travels in air. Now, we should note that as objects under free fall always experience what we call an acceleration due to gravity, which is constant and has a value of negative 9.8 meters per second squared. Now, let's try to look at different cases of free fall. Let's say an object is dropped from a height. So when an object is dropped from a certain height, its initial velocity is often assumed to be 0 meters per second because you do not give the ball a certain amount of force, you simply drop it. Now as the object falls down, we expect its velocity to increase as it travels the vertical axis. And this increase in velocity is due to, again, the constant negative acceleration of 9.8 meters per second squared. So by the time it reaches the lowest point, just before it hits the ground, its velocity final will be not equal to 0 meters per second and is way higher than its initial velocity. Now, for when an object is thrown upward, its motion starts at the bottom and achieves what we call a maximum height. Now, at the beginning of its motion, somewhere below, at the lower height, the velocity initial is not equal to 0 because you give the ball or the object an initial push. So its velocity is of a high value. But then, as it goes up, travels the vertical axis, its velocity will slowly decrease because of the acceleration due to gravity that is pulling it down, which is again negative 9.8 meters per second squared. So by the time it reaches its maximum point, it would have lost all its velocity, and the velocity at the final point or maximum would be 0 meters per second. So we will assume that at the highest point, upon reaching the maximum height, the ball will momentarily stop before it again falls back down to its original position. Now the other case is a ball thrown downwards. So there are instances that instead of dropping, you give the object an initial push as it falls down. So in this case, at the beginning of its motion, the velocity initial will no longer be equal to 0 meters per second because there's an initial push. And just like in the first case, as the object goes down, its velocity will increase as it travels down due to the acceleration due to gravity of the Earth. So there is this pull of the Earth that causes its velocity to increase as it falls down. Then by the end of its motion, as it reaches the final point just before it hits the ground, the velocity final will also be not equal to 0 meters per second and is way higher than the initial velocity. So those are the things you have to consider. Now, before we move on to the calculation part, I should also highlight that you need to know what is the value of the object's total vertical distance. And since we are now referring to the vertical axis, we will instead use the variable y when we represent distance traveled, or sometimes you can call this the height. Okay, a distance along the vertical. Now, moving on to the math part. These are the kinematic equations that I taught you last time. These kinematic equations use variables Vf, V final, Vi, V initial, and A as acceleration, T for time. There is also delta x, which is for the horizontal distance. Now, we will be tweaking or changing a few variables in the kinematic equation so that they align with the free-falling motion. So, for example, let's have the first kinematic equation. Vf is equal to Vi plus At. In free fall, we will change the variable A to G, since we have a constant acceleration of negative 9.8 meters per second squared along the vertical. It would be appropriate if we will use the variable G for acceleration. So the first kinematic equation will be V sub F equals V sub I plus G T. Again, instead of A, we will be using G. Moving on, second kinematic equation. So the second kinematic equation has the variable delta x, or the horizontal distance. So since free fall is about vertical distance, we will be using delta y equals V sub F plus V sub I all over 2 times T. Alright, so here, the only variable we change is delta y. Okay, next, kinematic equation number 3. We have also again a delta x. So instead of delta x, we will use delta y. And then we'll copy V sub I T plus 1/2 GT squared. Now notice that we change A to G once again for kinematic equation number 3. And for kinematic equation number 4, we have V sub F squared equals V sub I squared plus 2 G delta Y. So note that these are the changes, the delta Y and the G. So these are now the new kinematic equations that we will use when we are solving for free falling motions. Okay, so let's try to have a sample problem. Let's say a coin is dropped from a height of 4 meters. How long does it take for the stone or the coin to reach the ground, and what is its speed when it reaches the ground? So it is best if we imagine the situation first. So let's say from a certain height, we will be dropping a coin. So the coin will travel the vertical distance and reach the ground. We should note that some values are given. So the vertical height is equal to 4 meters, and that's the only value given. Also, as I've mentioned earlier, in free falling motion, there is always a constant acceleration due to gravity, which is negative 9.8 meters per second squared. Although that is not stated in the problem, you should always consider this value because this is a constant variable. So, with this info, can we immediately solve the problem? If you think about it, there is also another variable that is not stated as a number, but if you read the question properly, you should be able to note what that value is. That would be the velocity initial. Since the object is dropped, we can assume that the velocity initial is 0 meters per second. Note that this is not stated as a number, but this should be identified by you. Okay? So, given these variables, let us solve the problem. So, in the problem, we are required to solve for number 1, the time it takes to reach the ground, and the velocity when it reaches the ground. So that would be the V final. These are the variables that we need, so we have to check our kinematic equations and identify which of these equations are appropriate for the two unknowns. So let's say unknown number 1, which is time. So you can either choose first, second, third, but always choose the equation that will be shortest and most efficient to use. So if I will observe the equations closely, I would say it's the kinematic equation number 3. Okay, so why? If you look at kinematic equation number 3, kinematic equation number 3 has delta y, which is something that we know already, velocity initial, which is 0, g, which is a constant, and the variable time, which is the unknown. If you look at the kinematic equation 1, if you considered it initially, you'll notice that it has v sub f, which is not given in the problem. So we cannot use this. The same goes for the fourth kinematic equation. So let's just use kinematic equation number 3. Kinematic equation number 3 is delta y equals VIT plus 1/2 GT squared. Now you should note that the velocity initial is 0 meters per second. So if we substitute that here and multiply it to t, the value would still be 0, so we can remove that out of the equation. Therefore, our equation will be much shorter and it will become 1/2 GT squared. However, notice that t is the unknown and it is not yet isolated. So, you simply derive the equation, and once you do the derivation, you'll get t equals 2 delta y all over g. But there's an initial square here. So to remove that, you extract the square root, and t will become the square root of 2 delta y all over g. Okay, now to summarize or to review the derivation, first, notice that this is a fraction, 1/2 is a fraction, so if you cross multiply, 2 will be multiplied here to delta y, that's why we have a 2 delta y here, and then we still have a g on the other side, so we divide everything by g, that's why we have a g right here. Okay, and this is our final working equation. Alright, so all you have to do now is to substitute. T is equivalent to the square root of 2 times the height of 4 meters divided by the acceleration due to gravity of negative 9.8 meters per second squared. Please note that you cannot divide or extract the square root of a negative number. So this should also be a negative value. Now why is it negative? Looking back at our previous illustration here, the object's motion started here and traveled the vertical axis. Okay, and it is downwards. So if you will extend your coordinates or Cartesian plane, this is where the origin is, and anything below it would be negative. So this is like the negative y-axis. So our 4 meters here should be negative. So in terms of direction, the vertical value of the height is along the negative y-axis. Thus, the 4 meters here should be negative. And so if you divide two negative numbers, the negative signs would cancel and the value inside will remain positive. If you input this in your calculator, the answer that you will get is approximately 0.9035, or if rounded off, 0.90 seconds. So that is the amount of time it will take for this coin to reach the ground. Now, how about letter B? The speed when it reaches. Okay, so we will again observe, okay, the kinematic equations. And we are looking for VF. And there are kinematic equation 1, 2, and 4 with the VF. So again, always choose the equation that is more efficient. So if we consider kinematic equation number 4, it has VF, which is what we need. We have the VI, which is 0. We know the value of G, which is constant, and the value of the height. Now, might look complicated, but this is actually the best equation that we can use. If we consider this, okay, this is way shorter. However, it has a variable time, which is something we just calculated earlier. So just to be sure, I recommend you not using this equation. Nevertheless, it is still a correct equation if your value for time is correct. And yes, that's it. Okay, so if we look at our figure, where is the V final? The V final would be right here, okay, just before it hits the ground. Okay, so that is the value that we are looking for. Don't assume that the VF will be 0 because it will be touching the ground. So we are looking for that final velocity just before it touches the ground. Okay, so again, we will use the fourth kinematic equation, that is VF squared equals VI squared minus plus 2G delta Y. Okay, so we simplify the equation first. Again, the velocity initial is 0, so we can cancel this out of our equation, and our equation will become shorter. VF squared equals 2G delta Y. Alright, now to further simplify, we remove the square. So you extract the square root, and you'll have a final equation of VF equals the square root of 2G delta Y. And then you can just simply substitute the square root of 2 times the negative 9.8 meters per second squared times 4 meters. Negative 4 meters. Hang on, let me just correct that. Times negative 4 meters. And then, if you type this in your calculator, you will get a value of approximately 8.854 meters per second. But if we will round off, our velocity final is approximately 8.85 meters per second. And that is it. That is our answer. These are our answers for this problem. Okay? And that is all for this video. Thank you for listening.